So we're going to book says it's beyond the scope, but in for a monatomic molecule, there is something called the degree of freedom. So think about it's free to move in what direction, or what is it free to do? How many different options does it have? Yeah, it has three options. It has the x direction, the y direction, and the z direction. So in its energy, when you find its energy, you have its kinetic energy is 1/2 mv squared. When you say v squared, it's the x component squared and the y component squared and the z component squared. So we have three terms that happen to appear quadratic in the something squared. So we say it has 3 degrees of freedom if it's monatomic, because it can just move in the x direction, the y direction, the z direction. It can rotate about itself, but it's a point particle, so that doesn't contribute to the energy. Okay? Is that clear? All right. So basically, it's this: it's number of degrees of freedom times 1/2 kb times t. So each degree of freedom is worth 1/2 kb times t, and we have 3 of them. So in total, it will be 3. This is each degree of freedom is worth 1/2 kb. Okay. Now, what if we have that? Yeah, so let's see why diatomic is 5. Yeah. Diatomic. I thought we have a model. I don't have one. I should have got the chemistry. I didn't. But here is one. Imagine there is a molecule here and a molecule here. They're connected by a bond. So I don't have the 2 molecules, so it's your imagination. Right? 2 molecules. So it's diatomic. The molecules they can move in the x direction, the y direction, and the z direction. So they have 3 degrees of freedom translation, right? That's 1 degree. Those are 3 degrees of freedom. What else can they do? Well, they can rotate about their own axis. Yes. This is this axis this way. There is an axis this way and an axis this way. Rotating about this axis is worth 0. Why? Well, they are point particles, and there is no energy in this one. So they 1/2 I omega squared. Remember, moment of inertia times the angular velocity squared. The moment of inertia would just be 0 about this axis. Okay. So this axis, there is no degree of freedom. It doesn't count. Then there is this axis. It can rotate about this one, and it can rotate about this one. It can rotate about an axis toward the back, like this, and an axis vertical, like this. So how many degrees of freedom did we add? 2 more. So what's in total? 5. There is a third, there is a 6th one, but it doesn't kick in until several thousand Kelvin, about 5,000, 6,000, 4,000. And that's this one, vibrational. And vibrational, you can have potential energy, 1/2 kx squared. Right? It's like a spring, kx squared. That's a 6th degree of freedom, but we're going to neglect that because it doesn't happen until it's several thousand. So think about 5,000 Kelvin. I forget what the temperature steel melts, but it's beyond it. So steel will melt. So from practical point of view, we don't really care about it. Because if you have a gas, and to reach that into your car engine, well, the engine will melt. So you don't really care about it, at least for practical reasons or everyday reasons. So it would be 5 degrees of freedom. So for diatomic, yeah.
So you can like rotating the x plane and the y z plane.
Okay.
But then how come not the x y plane?
Its own axis is going to be 0.
So I mean, like in your 2-dimensional rotation,
Yeah.
if you're going like this,
Yes, that's one.
but then isn't there also like the Y Z chart?
So there's that one, okay, two.
And then what do you have
How
from?
about its own axis? So you have, here's an axis through it. So it can rotate about this axis. That's one. Let's say this is the axis. That's one. There is this axis, it can go about it this way. And the one that points to the back.
So you're saying that its axis of rotation will always fall on one of the x-axis axis?
We can choose that. So you can describe space with three axes, yeah. So this one does not count, the one through. So let me write this one before I forget. How many degrees of freedom again? We said we have 5, so it's going to be 5. And then times 1 half. Well, it would be 5 halves. Okay. C. And if you calculate the total thermal energy, it's going to be this would be 5 halves. So the total thermal energy is going to be 5 halves. And on T, which is N times 5 halves, R times T, which is N that's the thermal number. And the change was I see some question. Oh, okay. This is fine now. Okay. So, monatomic, diatomic, and what's the point of what we talked about today so far? Huh? So we looked at, we said we usually measure the temperature. It's a macroscopic thing. So now we have a microscopic interpretation of temperature. We can relate it to what's going on microscopically at the small, at the particle level. They're moving at certain speeds that are directly related to the temperature, or their kinetic energies, they're proportional to the temperature. That's the point. So macro connection. Now, we're going to discuss how heat flows between one system and another, and that if heat flows from this system to this one, if this one loses 10 joules of heat, this one will gain 10 joules of heat, assuming there is no work done. So we're going to look at that also from a microscopic point of view. I'm going to do it for monatomic. I think in the homework you have a mixture of monatomic and diatomic, so you would do that. I forget which homework it was, maybe 2? Homework 2? Yeah, you encountered that? Okay, it's in homework. All right, so let's, can I erase here?
Yeah.
And then I will.
Bless you.
So we're going to have 2 monatomic gases. They're in a container. The container is going to be insulated, and it's going to be rigid. So this container cannot change its volume, therefore the work done is 0. Okay? So we're going to ignore work. Now we'll have system 1 here. And it has number of particles 1, and its initial temperature is T1 initial. And this is system 2. And the number of particles is 2, and the temperature, temperature is T2 initial. So heat cannot flow from outside into this system. But heat can flow from here to here between the two. They're separated here so that the particles don't move. The right side will always have N2 particles, the left side will always have N1 particles. But they can collide through this thin sheet. They can collide. And so what happens afterwards? Let's say this one is 100 degrees Celsius, and this one is 0. Eventually what happens? They will reach some thermal equilibrium, right? And what would the final temperature be? Somewhere between 0 and 100. How much is it? Well, it depends on the number of particles on each. So we'll do it with just symbols, and then we'll do an example with numbers, and then we move on. So the question is basically, there will be some T final, and we would like to understand how much heat this one loses, and maybe how much heat this one gains, or maybe this one lost heat. It depends. If this temperature is larger than this one, then this loses heat and this one gains heat. We would like to understand how things go. Microscope. All right. Okay. So let's find. We're going to assume monatomic. We're going to ask, what's the total energy of the two systems? Well, it would be the total energy of system 1 plus the total energy of 2, right? Initial. And the total energy is going to be constant. The total energy of both of them combined is going to be constant. Do you know why? No heat enters the system and no work is done on the system. The way to change the thermal energy is to either do work or add heat or do work. We're not doing work, we're not going to change the volume, and we're not going to add heat from the outside. So this is going to remain constant. So sum of the two. So the total energy E1 initial is going to be 3 halves and 1 kB times E1 initial, right? Yes? And then for E2 initial is going to be what? 3 halves and 2 kB times E2 initial. I have a question. If system 2 were, let's say, diatomic, what would I change here? This would be 5 halves, this would remain 3 halves, right? If one of them is monatomic. So that's what you have to think about when you're doing that. So that is that.
Did you accidentally put in CP2 for the time? Is it possible? Because then how does the 3 over 2R equal to 5 over 2R for the n times fraction R T? I mean, don't people in CP2?
Oh, this is CV for diatomic, that's CV for monatomic.
Oh, okay.
Yeah.
Thank you.
Yeah, so CV for diatomic is 5 halves. So when they finally come to equilibrium, what's their total energy? Would it? Wouldn't be 0. The heat exchange would be 0. When they finally reach equilibrium, there would be no heat flowing between 1 and 2. But the molecules in 1 will still be moving, the molecules in 2 will still be moving, so they still have total energy. And it's still some number. And it would be equal to this number, it's constant. But I would like to write it in terms of the final. So it's going to be E1 final plus E2 final, right? And that's going to be 3 halves and 1 kB times T final plus 3 halves and 2 kB times T final. Notice I didn't say T1 final or T2 final, just said T final. It will reach some final temperature. And this is going to be written as n1 plus n2 times 3 halves kb minus 5. This is 5. E total. Yeah, because the 3 halves kb, they're all common, so which is fine. Now let's write E1 final in terms of E total. Look at E1 final. It's N1 times 3 halves K dt final. So, but T total has N1 plus N2 times this. So how do I want to write something times E total equals to E1 final. What would that something be?
N1 over N1 plus N2.
Yes, yeah. So I need to divide by N1 plus N2. That disappears. And then multiply by N1 to make it look like this. Yeah. So it's going to be N1 over N1 plus N2. Just algebra. So if you're not, this doesn't make sense, multiply this by this expression and see what you get. You will get this expression. Just double check. And then how about E2 final? You can guess. Anyway.
N2 over
Yeah.
N1 plus N2.
Oh. Yeah. Now let's see what the heat exchange is, what Q2 is, and what Q1 is. Or compare Q1 to Q2. What do you think the relationship is going to be between Q1 and Q2? Should be the same, yeah. They should be negatives of one another. One loses heat. If heat flows from 2 to 1, so let's say 2 lost 10 joules of heat, 1 should gain 10 joules of heat. So they should be negatives of one another. So we want to just go through the algebra and then show that. So let's do that. So we have Q2, which is the heat that lost or gained by system 2, will be what? How does it relate to its change in energy? How do I find how much heat it lost or gained? Huh?
NCV delta T. NCV delta.
NCV delta T. NCV times delta T. Okay. How about in relation? Yes. How about in relation to the thermal energy? The
Thermal
initial
energy
heat time.
plus work.
Okay. And how much is the work done?
0.
0. So it's just the thermal energy. It's the change in thermal energy with the heat. So it's going to be this. It's E2, the thermal energy at the end minus the thermal energy at the beginning. That's what I was thinking. Yes. It's a change in thermal energy. That's the heat it lost. Yeah. And so I'm going to work with this. So E2 final is this. I'm going to write that. So E2 final, I'm going to write this. N2 over N1 plus N2 times total. And then minus E2 initial. Minus E2 initial. Now E2 initial is equal to E total minus E1 initial. Yeah. E2 initial, just move this to the other side. It's E total minus E1 initial. So E2 initial E total minus E1 initial. We're going to continue paying this. So Q2 N2 over N1 E total minus E total. You can factor E total and you get this. N2 over N1 plus N2 minus 1 times E total. And then minus minus equals plus 1. N2 over N1 E total minus E total. When you factor E total, what's left from this one is just 1. Okay, so let's simplify this. What does this simplify to after you do a common denominator? N2 minus N1 minus N2. So what does that end up being? What does it end up? This one?
E2F,
Huh?
E2F,
E2?
F, final.
But I want to just simplify this fraction. Yeah. This is going to be, when you make common denominator, the common denominator is going to be N1 plus N2 squared. So N2 minus N1 minus N2. So that's just going to be minus N1. The N2 cancels the other N2, which is 1 minus N2. And then E total. Plus E1 initial, getting there. So this is equal to, I'm going to factor the minus sign, so negative N1 over N1 plus N2 times E total minus E1 initial. Now what is N1 over N1 plus N2 times E total? It's E1 final. It's E1 final. So we would have negative E1 final minus E1 initial. So let me just continue here. So Q2 E1 final minus E1 initial. But what's E1 final minus E1 initial? Yeah, so it's negative Q1. So Q2 is equal to negative Q1. So the E plus by 1 is equal to the E gained by the other, which makes sense as we prove it. The concept is repetitive. This seems like a lot of symbols. We're going to do an example with numbers. Okay? Any examples we're going to do with some numbers. Okay, ready for the example? Yes? Okay, very good. Can I raise this board?
Yes.
Got this?
Yes.
Okay, I'll wait 1 second. So, here's the example. We have helium and argon. Choice is because they're both monatomic. Okay? So helium, we have half a mole of it on this left side, and it's at 300 Kelvin initially. half a mole or 300 kelvin. The argon is also monatomic, but we don't have half a mole, we have a quarter with less molecules. This, but the temperature is higher, it's twice. It's 300 kelvin instead of 600. I'm sorry. This one is 600, this one is 300. I got confused. You let them for a while, they will come to some final temperature. And I ask you several questions. What's the initial thermal energy E1 for the helium? How about for the argon? And then what's the total thermal energy? And then what's the final thermal energy for 1? What's the final thermal energy for 2? And then what's the final temperature? And what's Q1 and what is Q2? So let's start with E1 initial. How do we find it? Huh? Yeah, E1 initial. How do I find E1 initial?
Plug it in.
3/2, yeah, plug it in. 3/2 N1 R times T1 initial. See, in this case, it's more convenient to use the number of moles times R instead of the total number of molecules times KB. Because I'm given the number of moles. Why do I need to convert it to multiply by Avogadro's number, multiply by KB? So this is more convenient. And then, so we get 3 halves, 0.5 for the number of moles, 8.314, and then 300. So E1 initial, so we get E1 initial to be, you should calculate it, and you should get approximately 1,870 joules. Okay, 1,870. Okay. Maybe I forget what this. Maybe decimals probably, but let's just. Let's do E2 initial. It's going to also be 3 halves N2 times R times T2 initial. Okay, I will give you a moment to do it. If you're paying attention to the numbers, you don't have to do a single calculation. You should be able to get the answer. What should the answer be? Same, because you double the temperature, it would be 600, but the number of moles is half. It's a 0.25 instead of 0. So this is half, this is double, so it's basically the same. So you plug in the numbers if you want to triple check, but it's going to be 1870. Okay. So what's the total number? What is the total energy? The sum of the two. Yeah? It's the sum of the two. That's the total energy. It's going to be 1870 plus 1870. And 1870 plus 1870 is 3,740, right?
Yeah.
So that's so we answered these. Good. Now we really want to know the final temperature, and we want to know E1 final and E2 final. How are we going to do that?
E1 final is equal to N over N1, or N1 over N1 plus N2.
So you're saying N1 over N1 plus N2 times E total, right? Just because of what you said earlier. Okay, but these are capital N's, not little n's. Does it matter? Homework? Show that. It turns out it doesn't matter. But let me show you why it does not matter. How do you get the total? If you're given the number of moles, how do you get the total number? Multiply by Avogadro. So here's why that's the case. Yeah. So N1 is just the number of moles, or N1 times Avogadro's number. And then on the bottom, N1 is number of moles times Avogadro's number. And then N2 is number of moles for 2 times Avogadro's number. And then the total Notice everything has Avogadro's number, so you can just factor it and cancel. So yeah, you get it's n1 over n1 plus n2. The total. It does not matter, yeah. So it works out nicely. N1 is half a mole. The total energy we said is 3740. So let's get E1 final would be, we need to multiply that. 3740. Yeah. So we need to multiply that. Give you a moment. You tell me what you get. Maybe about
2,490.
how much?
2,490.
Yeah, yeah. So 2,493, I guess, or 90 if you want to round up. Okay. So that's E1 final. How about E2 final? What do you do? I left you calculate that. For E2 final, you would have what? Instead of, yeah, it would be N2 on top.
Yes.
That's all. N2 on top. So you do that, you should get, well, basically half of this. Half of that is 1247 more or less. 1247. Okay? 1247. Again, we may differ by a joule or two if you round out or down from the decimals. But the important part of is the process. Okay? Now, how do I get Q1? What do I do to get Q1? How much heat entered into system 1? How much energy did system 1 have? How much energy did system 1 have? It had 1870. But now it has 2493. Where did the extra energy come from?
From
System 2. Heat flowed. So how much heat flowed? The E1 final minus E1 initial. Right? It's the change. There is no work in this case. So it is E1 final minus E1 initial. And so if you do 2493 minus 1870, it's 623. For Q2, they predict it should be minus 623 joules, but you can double check it. It's E2 final minus E2 initial. Should be about 623. Yes, 623. And oh, I found. We need to find the total energy. The final temperature. Before I find the final temperature, I want to mention, although they both had 1870 joules initially, they had the same amount of energy. Both of them had the same amount of energy, but heat still flowed from the higher temperature to the lower temperature. The reason is this. If this one is hotter and this one is cooler, why do they have the same energy? How did they have the same thermal energy?
difference in the moles.
Yeah. So yeah, these are moving slower, but you have twice as many as these. So in total, they ended up having the same energy because you have twice as many. Okay. So yeah, they have the same total energy, but heat doesn't care about that. It cares about the difference in temperature. They have a difference in temperature, so the temperature of the heat will flow from higher to lower. And it did. This one gained 623, and this one lost to 623. What's the final temperature? It's going to be somewhere between 300 and 600. As you're doing things, problems, you should see if it makes sense, right? If you get, let's say, the final temperature to be 700, you know that something went wrong. Probably you plugged in something incorrect. All right. So we will do this. We want to find the final the temperature. We know that E1 final is equal to 3 halves N1 times R times T final, right? So we can find T final that way. So T final will equal to 2 E1 final divided by 3 N1 times R. So we have 2 times 2493. Three 0.5 moles, 8.314. So the final temperature is 400. So it's not going to be just the average of the two temperatures. The average is what? Is it seems if you add them divided by 2, you're going to get 450. It's not. It's 400. And then, can we use E2 final to find it? Of course. So you have E2 final. You can have to, or you can say E final is equal to E2 final divided by 3N2 times R. And it will stay equal. Any questions on this? I hope with the numbers became, they were good. Okay, so officially done with these. The next unit is going to be heat engines and refrigerators. That's what I'm going to discuss. So, does anyone? So when we discuss heat engines and refrigerators, there's only one thing, one more law that we're going to discuss, actually the second law of thermodynamics. You notice conservation of energy requires, if this one uses energy, we have to account for it, and so this one gains energy. Would it violate conservation of energy if 100 joules flowed from the cooler one to the hotter one, to make the hotter one hotter and the cooler one cooler? Would it violate conservation of energy? No, it does not. It doesn't violate conservation of energy. Energy is still accounted for. It just it did not disappear, right? 100 joules disappear from here, they appear here, that's fine. But it does not happen, right? If you put hot coffee next to cold coffee, the cold coffee doesn't get cooler and the hot coffee gets even hotter, right? It doesn't suddenly, this one starts boiling and this one freezes. Does not happen. What happens is they go to some average temperature